This is a presentation of SBE 15, New York City.
Obviously, I have some experience in your organization way back in the past. Introduce myself a little bit. George Sullivan. I have a reasonably decent short bio over on QRZ.com. But basically, I got interested in electronics and radio and stuff when I was in high school. And the story was real quick, is that I was a paper boy and I was making $5 a week, which in the mid-60s was a pretty decent wage for a 12-year-old kid. But I decided I needed more money. Who wouldn't? And I had been interested in electronics. I had been getting a Popular Electronics magazine, and that certainly piqued my interest. And what happened is that I figured, well, maybe if I got a radio license, people might give me a chance. So I got some books out, I studied, had to learn the Morse code for the ham part of it. And I managed to pass my technician license on the ham side. And I managed to get my FCC first class license on the commercial side. I was in high school, so I was in my mid-teens at that point. Couldn't drive a car, but I had a first class ticket. And it worked out. And I went around to the local radio stations in my neighborhood, literally on my bicycle. And I hit WHLI, and they liked me. I hit WLIR, they liked me. And I hit WTHE, which was in the process of changing gears to a religious organization, of which I was not a member. And I guess they wanted people who would believe what they believed, but I believed in electrons and protons and stuff, and they had other things in mind, more like incense and so on. So that didn't work out. But the fine folks at WHLI called me and invited me to come over, and told me I could start, basically whenever I wanted. And I said, well, hey, I could start, but let's talk about hours, because I'm going to school. And they said, oh, we wanted you full time. And just didn't work out, because they needed somebody full time. And I was not even a college student, I was in high school. So then I called up WLIR, whom I had found. They had literally just moved. They were wiring their studio. And the guy who had been wiring their studio had quit. So I walked in I got lucky. Walked in at a very opportune moment. Hey, I was a kid. I was just learning. They gave me a really quick test, and the owner of the station himself, a gentleman named John Rieger, hired me. So I became an engineer at WLIR on Long Island. And this was back in 1968. Anyway, took me a while. Worked there over some summers and learned how to do stuff. Worked in the studio, worked doing recordings. We made plenty of live recordings then from my father's place. And we had to deal with ultrasonic recording studios in Hempstead. So I kind of liked doing that. The problem was I really liked classical music, and they were into the avant-garde rock. So there was a little bit of a mismatch there, but it worked out. In any event, by 1972, I became WLIR's chief engineer, and I kept that job until 73, where there was a change of ownership, and the new owners brought in their own people. So I kind of said bye-bye. So there we go with that. So anyway, let me change gears here just for a moment. Yeah. You guys still hearing me all right? Seeing me?
Yep.
Okay, good. From WLIR, and by the way, at the time I was with WLIR, I had graduated from high school, and I started going to college, and I was going to Hofstra. So where Andy is sitting right now, hey, I was a student, well, actually I was there before they put the building up that he's in. But I volunteered at their radio station, which was WVHC at the time. And I did some stuff there. And got a new job full-time working at Fairchild Space and Defense Systems in their RF lab, which was a great position for a ham operator. So I got to play with all the latest and greatest electronic goodies. And we were making EMI receivers. So we were doing direction finding. We had computer controlled radio receivers. I wouldn't call them SDRs, but they were sort of the predecessors of it, where we had a Hewlett-Packard mini computer with toggle switches hooked up to a radio that had a parallel interface to its frequency synthesizers. And we did that. And in the meantime, I was hamming, learning how to build repeaters and stuff. I did that. Eventually, they sent me over to Japan and Korea so I could work on their equipment. Did that. Learned how to build direction finding systems at HF. We had things called Wollen-Weber antennas, which were 800-foot diameter circles of 200-foot towers. They used to call them bird cages. A Wollen-Weber array. That was kind of neat. So I learned about those. Did some of that. Then I went to work for Telecare, which is here on Long Island. It was run by the Catholic Church, and it was their television organization. It was ITFS system, and I got involved with that starting around 78. Became their chief engineer, and had that job until 81, when I started working for Grumman. And I worked at Grumman for a really long time, from 81 until 2015. From sometime during my time at Grumman, they liked what I did, so they sent me to school. So I got my master's. I got my master's in telecommunications from what is now NYU, but back then it was called Polytechnic University. And before it was Polytechnic University, it was called Brooklyn Poly. So I have a reasonable academic background there. And basically, while I was doing that, I started working for Channel 21, WLIW television. It was a part-time thing. I'd work at Grumman full-time during the day, and then I'd wander over to WLIW television at night, where I was their primetime master control engineer. And I did that from 80 to 87, and I guess here you can see my SBE.
Oh, your screen share is not up.
Oh, I'm sorry. Let me put my screen share up. Thank you for telling me.
Mm-hmm.
All right.
We were admiring your TIAC though.
Oh, okay. Okay, so here you see my SBE, which I joined along the way. But in 1987, I was going for my master's, and it was either keep my night job and flunk out on the masters, or do the masters and kind of like say goodbye to income for a while. So I said goodbye to income for a while, knowing that the other end looked good. So we did that. And along the way, I joined IEEE. I'm now a member of the IEEE Consultants Network, and we do lots of good things there. So let's get out of that. I've always been doing ham radio in the background, and in 2008, I upgraded from a technician class license with Morse code to an extra class license, which was a nice leap. I passed the exam one shot, and rejoined LIMARC, which I had been in briefly in the early 70s. And LIMARC liked me. I liked them. It was a good fit for them. And I worked my way through the organization, being on the board of directors, and worked my way up to vice president, where I am now. So without further ado, let's see what we can do with our little thing here. Any questions on where I've been? All right, let's see if I can share this again. All right, so, whoa, everybody see this?
Not yet.
Not yet.
Hang on a second, why isn't this working? You see it now?
Coming through now. Yep. Anatomy of a repeater.
Okay. Yeah, we have talk about what we call anatomy of a repeater site, which is all the stuff an organization has to go through to put in a repeater. And I'm using ham repeaters as an example, but you know, I don't think there's too much difference between what we do and the commercial guys. And also, I think there's a lot of applicability to the broadcast industry because this is a lot like a broadcast station, except this also has a receiving function, which typically a broadcaster just blasts out from wherever they are. And in fact, we share a lot of the same sites. So anyway, here we go. Talk about a repeater. Okay, first of all, here's our agenda for the day. Let me ask you a question. Can you guys see the far right side of this slide?
We see agenda and all of the bullets, and we see the pyramid picture
You do, okay,
with all the repeaters. There's like
Okay,
2 on
yes, I-
top and 3 on the bottom.
good. Okay, that's wonderful because on my screen, I have participants' videos. So I have little vignettes of all our videos on the right.
Yeah,
Yeah,
they're
no,
going to be there.
you're
You can
coming
move
through,
that-
though.
you can Move that around.
Good, okay, that's fine. Okay, so basically gonna talk to what is a repeater, you know, how far does it go? The complement to that, which gets asked every day, several times a day, how am I making the repeater? For you guys that are hams, you'll recognize the comment. Talk about the site environment, because where you put it is really important. Talk about antenna systems, because that's the single most important part of the system. You know, what powers these things? Where do we get our power from? The receivers, transmitters, controllers on the repeater. We'll talk about linking. These days, many repeaters don't stand by themselves. They're part of a network. And we'll talk to that. We'll talk about security because that's becoming more and more important. Laws and regulations drive a lot of what we do. And we'll talk about some future references, future directions, and I have some references. So let's go. Okay, from the process of having a repeater starts with, you know, what do you want it to do? Where does it need to work? So we'll do what we call coverage design. Then we'll go up to let's build a repeater. What equipment do we buy? Where do you put the antenna? What does the RF path look like? How does the users get to it? We'll have some access parameters. When you're using the repeater, you know, this is an operational thing. How do you hand off from one guy to the other? And then once the repeater is there, what do you do to make it better? So we have optimize and tuning it. So that's pretty much the story of a repeater. On the left, we see a very popular type of antenna. On the bottom, we see a commercial repeater. We see a Icon repeater and a Yaesu repeater, the two leading ham brands on the top. Motorola, which is certainly one of the leaders, along with Harris, for commercial repeaters. And here we see Bridgecom, which is an up-and-coming company, which is selling digital repeaters for ham use. And on the bottom right is the Kenwood repeater, which is, I'm afraid it's a fading star. Wish it wasn't, but it seems that way. Okay, so what is a repeater? I think you guys have a pretty good handle on what it is. So it's a combination of a receiver and a transmitter so that the receiver picks up a signal and it retransmits it at a higher elevation. And the basic job is to allow radios without line of sight communications to communicate. Most repeaters use two different frequencies. The mobiles transmit on one and the repeater receives them and retransmits them on another. Okay, great. And another characteristic here is that the signals are all line of sight. So the repeater generally has to occupy a really nice place in the environment, nice and up and down the hill. And it's simultaneously transmitting and receiving. It's probably, in most cases, going to use the same antenna for both. We need really high Q RF filters, and this is what's different between a repeater and the home ham radio station, that are going to prevent the repeater's receiver from being overloaded by the transmitting signal. Okay, and then we have auxiliary connecting features that attach repeaters to each other. Internet, the most common thing today, IRLP, Echolink, All-Star, AutoPatch, voting receivers, and RF links to other repeaters so that we can make networks out of these things. On the bottom below our conceptual picture, we have a sort of a block diagram. We have an antenna, lightning surge arrestor, device called a duplexer, which allows us to connect the antenna and to a transmitter and to a receiver without blowing each other up. And we have a power supply that gets from a power source. We have the internet and RF links attached to a controller. And the key thing here is that we have an audio bus. We have a carrier operated signal. This is COS. And we have a CTCSS, which is a tone activated squelch, which almost all the repeaters use these days. And that goes into a transmitter, into a power amp. And then you see a device called a circulator or an isolator, and that prevents intermod. And I'm going to have a couple of slides on that. Okay. Moving on. Hey, if you guys have questions, please just ask me as I'm going along. Okay. Okay, I hope everybody's staying awake. Okay, so the first thing is you're going to want a repeater. You know, where does it have to cover? You know, where are the folks that want to use this thing? So we want to determine where the radio coverage is required. So we have to look at line of sight because our signals use line of sight. They're VHF and UHF signals. How much power do you need? And who's already there? It's pretty rare these days, especially in our metropolitan areas, to find free frequencies to put another repeater. So typically, we look far and wide at different channels, different frequency bands, and so on. And there's even a ham group, and there's several regional groups that do channel coordination with us. So we have those groups working with us. With a repeater, the limitation isn't, at least not usually, the repeater itself. It's the ability of a small walkie-talkie or a HT, so on, is the limiting factor. And to show you what that means, here's my my little walkie-talkie. This device is by Baofeng. It costs a whopping $50 or so. It covers 3 bands, 2 meters, 220 megahertz, and 440 megahertz. And this is what the typical mobile user is going to be running. So that's the limiting factor. It's the power that these things can make and where they are that have to determine what you have to do with the repeater. So based on that, we have a 1-watt radio that gives us plus 30 dBm. It has a terrible antenna, which is a quarter-size rubber ducky in most cases, which is going to give us at best minus 6 dB gain. That's awful. So let's take the 30 from the plus 6. It has a receiver. They're going to tell you that it is so many microvolts. That doesn't work very well. So we have to convert the microvolts on the receiver to dBm. And here's the formula that lets us do that. Okay. Now we have to predict the signal strength and the line of sight distance. Okay. So from that, we have a factor called a little bit of math. This is not hard. It's actually very easy. This is called the Friss equation. Any of you guys use this Friss equation? You see this before? I'm seeing blank faces. Okay. This basically takes a signal, subtracts all the gains and losses from your antenna system, and then adds what we call the path loss to it. And this assumes that the transmission is going out as a nice circle. And we have the wavelength, the distance between the transmit receive antennas. The power is measured in dBm. And you just plug the numbers into this formula and it'll tell you if you have enough signal. The line of sight calculation is pretty easy. We have the distance in kilometers. This is how far you could go. It's basically 3.5 times the square root of the height of the transmitting device, the transmitting antenna, and this plus the square root of the receiving antenna. And this is a line of sight formula. Keep in mind that all of these formulas, you can carry them out to as many digits as you want in the math, but at best, they're approximations for the real world. So I wouldn't put a lot of significant digits into this. The next thing we have to do is look at something called the Fresnel zone. I have a slide on that. But here you see a typical RF path from the transmitter up on the hill to a device. In this case, it was a rooftop device, 25 meters high. Okay, and these red things here are trees and buildings in the area, typically called ground clutter. And this is showing you that this path was working. The free space loss was 108.4 dB. using the Longley-Rice attenuation model, and it would tell you what the the loss would be. And this sounds like it could get to be really difficult, but the good news is that we actually have some software that lets us do it. You may have the same stuff for your stations. So let's change the page over here. Okay. Again, talking with the equation, do we have enough power? And this is an estimate. We're not going to too cuckoo with the math, but the math is really pretty simple. Here we see we have the power at the receiver is equal to the power from the transmitter, plus the gain of the antenna on the transmitting side, plus the gain of the receiver on the receiving time, plus the path loss. So this is going to be a pretty big negative number. Lambda is the wavelength, D is the distance between transmit and RF and receive. The wavelength and the distance have to be in the same units. I suggest meters. Power is measured at the transmitter RF output jack. The power input into the receiver, which is over here, is measured at the receiver input jack. Okay, and as usual, 1 milliwatt is 0 dBm, which is standard. Okay, now we have to have some assumptions for this thing. Okay, so what does Mr. Frisk say? First of all, the distance is usually a lot greater than the wavelength. If it's not, we have what we call near field. And there's a whole different set of calculations for that, which really get ugly. But the far field has some nice approximations that we could do. It also assumes that the antennas are correctly aligned, have the same polarization. If they don't, we could lose 20 dB due to polarization mismatched. We assume that everything is in free space. We assume that there's no multipath, which means the signal isn't bouncing off a building. Yeah, right. Hope that that happens. The path is within line of sight and has adequate Fresnel zone clearance. The bandwidth is narrow enough so that a single value for the wavelength can be used to represent the entire transmission. Generally, a few kilohertz of deviation on 145 megahertz or so doesn't make any difference, significant difference in the math. Okay. All of these equations are referenced to isotropic radiators. And when you look at the sum total of all of these, and it's bottom line is that the ideal conditions that you need for this equation to work completely correct are almost never achieved. Because in ordinary communications, we have obstructions, reflections from buildings, and most importantly, reflections from the ground. Sometimes we even have reflections from moving airplanes. So what I guess I'm trying to say here is, yeah, do the math. It's important. It'll give you an idea if you're in the ballpark. But, you know, if your math is showing that you have 1/10 of a dB or a couple of dB, you know, try it before you 100% by the math. On the other hand, if the math is telling you that you need 100 dB more than you have, you know, go and try something else. Right? Good. Questions? Don't hear anything. Good. Okay. Well, what's going to help us do this is called path mapping software. There's a bunch of these packages out there. The commercial ones are probably better, but this is an open source freebie, free to anyone to use, and it's called Radio Mobile, and it's a Windows PC variety. And here we see the results of a repeater that we actually went and installed at Andy's facility over at Hofstra. It's in Tower C. It's a few feet away from his WRHU transmitter. In fact, I think if you stretch far enough, you could probably touch both of them at the same time and hope that there's not a ground loop so the current doesn't go through. Okay, and in this project, we relocated a repeater from the WLIW transmitter tower to Andy's site over here. And what you see here are screenshots of the information that you need to put into this particular radio mobile software module to produce the coverage map. And what you're looking at here is the actual inputs that we use to make this map that you see on the left. Okay, where green is actually a good signal, and yellow is a signal that at best is marginal and probably won't work too well. And the circle is your line of sight distance. Okay, so, you know, at the edge of the circle, you run out of line of sight. And here you see where we, let's see, where are we adding line of sight here? Transmitter power thing here. Let's see. Anyway. Oh, here it is. 2 rays for line of sight, meaning that you can use not only the transmitter height, but the receiver height as well. Okay, so the climate on Long Island is maritime temperate over land. There's a bunch of climate choices. Ground permittivity is based on Long Island. And these units here in the back of this thing as a supplement, I show the ground soil conductivity. And Long Island has the worst ground soil conductivity in the entire United States. So if you're going to think about getting a good ground out here, good luck. It's really going to be tough to achieve. Okay, and there's something called the Longley Rice RF propagation model for irregular terrain, which is embedded into this software. All right, and this is going to show you how far this thing can go. So here you see the limit, and you can probably tell from this that it kind of looks like outstretched fingers over here as we go through the North Shore on Long Island, hills and valleys, to where we have a good signal in some places and a really bad one at others. So let's blow that up and see why it is. So what I've done here on this picture, the same picture as you saw before, but this is a very much magnified view of it. So here you see where it's a good signal coming out of the repeater itself. And here you see that there are valleys. And here you see the good signal going through the middle of the valley, and it's blocking the signal. Terrain is blocking the signal here. This being Route 25A or so on Long Island. So basically, our repeater is getting out pretty good up to the North Shore, and places on the North Shore will work great, in places it won't. By the way, and not for nothing, this is very similar, if not almost identical, to the map of WRHU, which is Andy's station. So if you're wondering what the coverage looks like on the North Shore, it's going to look very similar to this. Wait, questions? Nothing heard. Okay, so we have some software to help tell us where this thing is going to go. Okay, now we have something called a Fresnel zone. And this is based on Fresnel lenses, which you might know because that's what lighthouses use. And those are those little bubble jars that have lenses on them that have circles going around. Again, the place where they're used is the lighthouse. But Fresnel zone clearance basically means that your signal, though you like to think of it as line of sight, it actually occupies an area, and it kind of looks like a sausage or a cigar going around. So if your signal strength is strength, it has a radius around it, and it has Fresnel zones, and they're all different integers. We usually calculate the first Fresnel zone because that's usually the limit. If you first Fresnel zone is penetrated by something in the middle, even if you have line of sight, Fresnel zone is going to keep it from being a good path. That's something you have to look at and be aware of. For you guys that are doing microwave work, I'm sure you know Fresnel zone because doing a microwave path is it's almost mandatory that you use a Fresnel zone to make sure that you have path clearance. Okay, moving along. Okay, here's another repeater, and this is a LIMARC. And just to confuse people, this was not done with the radio mobile software. It was done with different software. And for some reason, they decided to change the colors so that the yellow is now the good signal and the green is the mediocre signal. The line of sight is the radius of the circle. And where you don't see the circle coming through, going into Westchester and Putnam and beyond, it's being blocked by terrain. By the way, this repeater is up at Glen Oaks at North Shore Towers. It's a total of 183 meters above sea level, which is a terrific site. To those of you who live on Long Island, if you're using the Grand Central Parkway, the site is right at the border of Queens and Nassau. It's 3 apartment buildings. Tons of repeaters at that site, and there's a 92.7 FM on that site as well. That used to be WLIR. I know it well, but I haven't worked there for a while, and it has a different call sign at this point. Okay, so our line of sight path is roughly 30 miles from the building. The Fresnel zone coverage, I mean, it's taking 24 meters away from your height. So our site path is estimated about 42 kilometers to be a good path from a 1-watt walkie-talkie. And on Long Island, your good path extends out to about Route 231. After Route 231, which is Deer Park Avenue, this repeater kind of fades away. And we go to another repeater. Okay, is there a question? I hear something. Uh-oh, I can't quite hear you.
I think it was just background noise.
Okay, well, then I'll keep going. Yeah, any questions about where we're at so far? Good. Okay, we have to put a repeater someplace, and from what you can see, we want to put it in a nice high spot so that we have a good view of the area that we have to cover. Gee, that sounds a lot like a broadcast station to me. But same is true for repeaters. So here you see some repeaters. The repeater in the middle on the top is Santiago Peak in California. This is a high spot in the area covering LA. So guess what? Every radio organization on the West Coast has a site up here. And you can see how many different repeaters of all kinds. I see microwave, I see broadcast, tons of repeaters. The W6ATN is a television repeater in the ham community. That's up there as well. On Long Island, we see a tower in Plainview. LIMARC has some repeaters on this tower. LIMARC has repeaters on the Selden Tower, which you see over here. This is Glen Oaks. That was the repeater we just saw the coverage of. And this funny looking antenna over here is actually the broadcast station at 92.7. Okay, we have a room in the Empire State Building that we're sharing with the broadcast organization. This is up on the 79th floor. Now, I haven't been there, but I have the impression that this looks like a closet with a window. But from the 79th floor, it's beautiful. So this is a picture that one of our guys took looking out of that window, and there's a picture of the East River and going out over Long Island. Okay. So site environments are crowded. They have lots of services in them, and we all have to be good neighbors. That's going to be a theme. Okay, let's start by talking about antennas. Okay, one is standards, and we love standards. There's so many of them. But for the tower, and I found out that not many of us on the electrical radio side seem to know a lot about the mechanical standards here. And the TIA 222 antenna structural support is a huge standard that tells us how to design towers. Talks about wind loading and how to do wind load patterns, different types of towers. How do you do self-supports versus guide towers? Providing all the mechanical stuff you need to put up a tower and make sure it stays up under difficult conditions. So we're going to look at that. You can look at that standard on your own. I'm not going to cover the actual standard here, but I'll talk to some stuff from it. Then we're going to talk to our antenna, which is important here. We're going to talk about SWR, the standing wave ratio of the antenna, its gain pattern, and something called beam tilt. We're going to talk about the coax that we use to bring the signal from the antenna to the electronic devices. And the coax is very critical. It's out in the environment, and it has to be ruggedized in various ways. And it also has to meet some electrical characteristics. How much power can it take care of? Is it going to lose the signal? What kind of connectors work with it? Do we want a pressurized thing where we put desiccated air or nitrogen or freon or something in it versus a dielectrically insulated coax? Okay, mechanical. When you're mounting the coax, where do you put it on the tower? What's the best way to take care of it? How do you prevent aeolian flexure? An aeolian flexure is the engineer's name for the Peter, Paul, and Mary. The answer, my friend, is blowing in the wind. So we have aeolian flexure. We have ice buildup. Yeah, in the winter months, that can be a problem, especially up on the tower. And we have something called shadowing, where the antenna lets the signal go out great, but the tower itself is making a shadow. We have environmentals. Lightning arrestor. You put a lightning rod on top of a tower, but my God, these things are in a high spot, and you want them to be as high as possible, but you just know it's a lightning magnet. So we have to talk about how do you deal with lightning, and then inevitably, where does the other end of the lightning go? To the ground. So we got to talk about grounding and bonding. So we see pictures along the side here of a lightning arrestor. It's a tiny little thing. It's not much bigger than a connector. But this can actually handle substantial amount of power, and it has a device in it called a gas tube. And if lightning should hit it, normally the tube is open, but if lightning hits it, it arcs over and conducts. Hello. It can do that so many times before it has to be replaced. This particular one is made by Polyphaser. and they seem to be pretty good. The top, middle and right, we see some different kinds of coax. We see coax over here, which is Heliax, that's a brand name, and it's air insulated. It has this Teflon spiral going through it. It has openings in it, and we can feed it with air. The air has to be dry. If it's atmospheric air, it has moisture in it, and that's just going to cause signal loss and condensation on the inside, and not good. Doesn't work well. Don't do it. But if you feed it desiccated air, which is air that we take the humidity out of, or nitrogen, or better yet, Freon, although I don't know how well today's version of Freon works, but we used to put Freon in these things because Freon is a great conductor of heat, and it keeps these lines running cool. At the ham level of frequencies, the most we can run is 1.5 kilowatts or so. Not much of an issue for heat on these things. But I was running WLIW television, which was running NTSC television with 25 kilovolts on a Klystron amplifier that has running 10 amps before we put the anode pulsar on it. 250 kilowatts into this stuff. That's a significant ton of heat. And the Freon really worked there. It's probably easier for a lot of us not to bother with filling these things with air, so we have dielectric coax. And of course, there's different kinds of dielectric, ranging from foamed electrics, which are great, but they melt easily and they absorb water like a sponge, to more solid dielectrics that lose more signal, but they're a lot slower to absorb moisture, and sort of all kinds of stuff in between. So here in the middle, it's not intended to be an eye test. You can look at it for allowing you to look at the different types of Heliax coaxial cable, and these are the specs for the foam dielectric. A little note over here on passive intermod, which is basically when you have lots of high-powered stations at a site, and I certainly hope that those pictures convinced you that that's pretty common. Nonlinear points, especially those that are ferrous, create interference frequencies like sudden differences, and they work as mixers. And they can have a terrible effect on your signal, so much so that you have to be careful of the connectors. And in fact, we strongly recommend that ferrous connectors not be used. Try and use plated brass. It works better, and it won't cause intermod. Okay, moving. Okay, so what can we say about the tower itself? And here I have some pictures. The picture in the middle with the berms, this is the WRHU tower. This is next to our repeater in Hempstead, New York. This is Constitution Hall, Tower C. And for you folks interested in WRHU, that's a picture of the antenna on top of your tower. And it's in a residence hall. It's in a dormitory building, so it's definitely controlled access. Okay, so out in the open up there, we have a hostile environment. The sun beats on this thing all day long, and then it comes at night, and then the sun beats on it, so it's expanding and contracting all the time. The wind blows, so we have exposure to the wind. In some locations, they're naturally flat or hilly, and there's a surface roughness, and you can get from the U.S. Geological Survey how much wind load is it exposed to. You can know what the normal wind loads are. We can do wind speed measurements, and we have to do that at a site using the 3-second gust method, which is ASC 7-95. So this is a federal standard for how do you measure wind speeds. And this is a 3-second gust is going to come up over here. For sustained wind speeds, which we get in a hurricane, 60 seconds average. So you can best believe that the peaks in a hurricane are a lot higher. That's used for our Saffir-Simpson hurricane wind scheme. Okay, gusts are all higher, so you got to give a generous percentage there for peak loading. Okay, so this is going to determine your wind load, which is how fast is the wind blowing. Okay, antennas blow away around in the wind. The stick type of antenna that you saw typically is supported on its bottom by a hefty thing, but that leaves the top of it free to spin around, and they often do. So what people do to stop that is they put an insulated outrigger from a tower, and they support the top of the antenna as well as the bottom. Now the top of that little outrigger support has to be insulated, you know, And you better hope it doesn't pick up ice or prevent ice one way or the other from building up on it. The same is true for your antenna. Antennas are subject to ice loading. So we have ice shields, and in this picture here, can you see my cursor moving around? Yeah. This structure on the top is just a little screen that keeps ice from denting all the coax coming up off the base of this particular tower. Ice shield, radomes. Okay, over here you see some heated radomes over here, and you see that this tower is, yeah, this is what icing is like on a tower. And here you see that you need the heaters because otherwise your antenna is going to get blasted by this kind of ice buildup. Okay, so you can put radomes. This is the WRHU solution, or you could put a heater. And in this case, it looks to me like it's a combination of a radome and a heater. Okay, FCC Part 17. That's a punt because that actually goes to the FAA. And that says about obstruction lighting and tower visibility. Okay, so let's talk a little bit about that since I mentioned it here. The tower paint, it's important. Believe it or not, the National Institute of Standards and Technology, formerly known as the National Bureau of Standards, they actually commandeered a DC-3 aircraft in the sometime in the late 60s, early 70s. They flew around the DC area, Metro Maryland, Metro Virginia, Metro Delaware, and they were looking at towers. And they wanted to see which towers had the most visible colors from the air. And they put them down in a chart, and they eventually agreed as to just exactly what color was the most visible from the air. And it became a government standard, and this is the standard for the paint chip. And that is that ugly orange color that you see all our towers painted with. It actually came from somebody who did a real scientific experiment to see what worked. So I was pretty impressed with that. Okay, material is pre-qualified steel to build your tower from. Not sure what all those pre-qualifications were. I was kind of unable to find a good link to that. Lots of towers are in earthquake zones, and you be careful of them. You have to build the tower the right way to withstand that. Fortunately, here in the New York area, that's not a major concern, but we do have earthquakes from time to time. That gets into tower foundations and guy anchors. So here you see a typical guy anchor over here. And over here you see the tower foundation itself. Picture of that particular tower is on the left. All of these pictures, the ones without the ice are the WRHU. So these ones across the bottom, these are all the WLIW Channel 21 transmitting site in Plainview out here on Long Island. Okay, soil pH and resistivity, which is what's your ground soil conductivity. It's important for corrosion control because you don't want sneak ground currents floating that can corrode your ground system. So we have to make sure of that. You have to check it every so often. I suggest annually. Check your soil pH, something that most of us probably don't do. And we hope the site owner does it. And typically they don't, hoping that we do it. Some places have flood zones. Certainly here in the metropolitan area, there's lots of AM stations built in the New Jersey swamps. So they have to deal with flooding situations in their towers, which means you need good drainage. Here we have a manhole someplace along the line at WLIW, but this is based on a sand hill, so the water just goes down and doesn't bubble. Ultraviolet solar radiation, the stuff is out in the sun, it can soak up solar radiation. That's not good. You have to make sure that you're free from UV. And you won't be free from it, but you got to make sure your stuff is UV resistant. And you got to fix it every once in a while because despite our best efforts, something will go wrong. Mr. Murphy says so. So we have to deal with things like cable bundles have to be reachable from the tower ladder. So you can look at the cable ladders as you're climbing and descending the ladder. That's why we put cables there, so they can be seen. Okay, fatigue basically is a function mostly of aeolian flexure, but also of ice loading and some other things, temperature cycling. And periodically, we get things that break that have to be replaced due to fatigue. And here's one I wish I didn't have to put here, but I'll talk to vandalism. Because when I was working for Telecare, we had a video repeater site out at the St. John of God Cemetery in Iceland, New York. And it was a lovely tower. It was a 280-foot tower. And we had a video repeater up there that would take the signals coming from our studios and repeat them to the Catholic schools in central Suffolk County. And what happened was it was a pressurized antenna system using EW20 waveguide running at 2.5 megahertz, 2.5 gigahertz, sorry, 2.7. That was the ITFS frequency band. And turns out that the blinking red light on the tower was like a prize for the local hunting club. So all the young kids in the hunting club took their 22s and aimed it at our tower light. And lo and behold, several times a year, this thing went out because people shot it out. I wish I had a cure for that, but I don't. So we were subject to vandalism. Unfortunately, along the way, they also shot holes in the antenna, which was a pressurized radome, taking its pressurization from the waveguide pressurization, and that didn't do good. So we had to replace an antenna someplace along the line, and asked for more frequent police patrols. It was a very difficult thing to control and fix. And to this day, I don't have a better solution to making it bulletproof. Okay, next slide. Okay, let's talk about the antennas themselves. The two main types that we find in repeaters are the vertical collinear, kind of looks like this. It's a fiberglass stick. You see these all over the place, very popular. Or a dipole, which is discrete elements that are wired in a phasing harness. The stick has the advantage of a sleek appearance. They can be hidden a bit better. They're aesthetically pleasing. The dipoles stick out a bit more. They're a bit more subject to ice damage, so beware of those. On the other hand, it's easy to control the pattern on these. And here you see our dipole, where you have a single dipole and it has a nice figure 8 looking pattern. But when you put all four of them lined up the same way as these are, you get a directional pattern. So the signal is stronger in some directions than others. So if this was in the middle of Long Island, this would be a good fit because Long Island is, slim and long. On the other hand, when Channel 21 first went on the air back in 1968, it had this pattern, but it was doing north and south instead of east and west. So we noticed that when we were doing some field strength meter readings, and Channel 21 had to have its antenna rotated 90 degrees so that its pattern would be correspond with what we had on Long Island. These antennas typically have a pattern that looks like a donut. They're basically omnidirectional. Here you see some specs on it. So this is a typical 2-meter antenna with 6 dB gain, which is pretty modest. Weighs 32 pounds, and it's basically supported on the bottom. That's quite a strain. That's why we want that overhead support arm, keep this thing from dancing. Okay, the return loss, this is the SWR on the antenna. Bill, WB2QGZ, ran this one for us, and here you see what the return loss on the antenna is. Okay, some sites, not many, but some do, they have what we call a master antenna system, in which they have broadband antennas, and they have broadband frequency splits, and they share the antenna among a bunch of different repeaters. So we have a series of bandpass filters, basically one RF path for each repeater up there with the distribution amplifier, and it feeds cavity receivers, bandpass cavities, one for each receiver. And then we have a master transmit antenna, which are combined, and no duplexer is needed because it's built into the RF cavity filters that are part of the master antenna system. And the combiner usually includes isolators and circulators. And that's it. Master antenna systems are custom designed for the site and for the services. Making changes to the site and or services on a master antenna is difficult. We typically have to get the manufacturer involved to do tuning and change elements out and so on. So these are pretty fixed. Once you have one of these things, you're kind of locked in. Okay, some notes on the antennas. Okay, it's the most important part of your repeater. And if that's not correct, nothing else is going to do it. The feed line is number 2. They're the most expensive. They're difficult to get at because they're high up. You need a climber or somebody willing to be a climber. And they're exposed to your hostile environment, and they require the most expensive maintenance. Now, Collinear antennas are more prone to what we call duplex noise. And the reason why is that they flex in the wind. And if the wind gets really strong, a lot of them aren't as strong as you'd like them to be, and they just snap off when they're combined with ice and hurricane or winter storm level winds. And this happens a lot. It's happened to LIMARC a few times. When I was a member back in the day of the Northeast FM Repeater Association, we almost had this being an annual event that we could expect an antenna or two to snap because of the ice and the wind. Okay, so here's a little ditty that tells us how to support it. And this picture over here, this graphic, is how to build your own collinear array. If you ever wanted to know what was inside one and what would work, this is the flexible Station Master. It was actually done by the people that designed Station Master antennas. And this is how you do it. It's just transposed sections of coax in a fiberglass tube. This is how you do it. This has all the lengths and how you tune it. It's 22 feet long, and it was designed to be put inside a 2-inch pipe. So if anybody wants to look at those, I remember spending a summer weekend rebuilding a Station Master. It broke on the inside. They don't like to be bent. You have to remove the guts of them, and believe it or not, the guts of this thing is actually beeswax. And we had to melt the beeswax out of it, pour it in a container, filter it, and when we were done fixing the antenna, we had to melt the beeswax again and pour it back in. And that's right, somebody back in the factory figured out the dielectric constant of that beeswax, and it was part of how you tune the antenna. Yeah, think about it. I was a teenager at the time, but I learned a ton from doing that. Okay. Moving on, okay. Well, hello. Where am I? Here we are. Okay. So when you have the dipoles, they don't have the duplex noise problem, but they can have phasing harness degradation. In other words, the coax connecting the different dipole elements to each other can suffer water damage. I mean, waterproofing does not last long. Joints in the coax, especially when they're blowing in the wind, doesn't last. Lots of manufacturers use various methods to weatherproof them. They often don't work well, or they work great for 5 years, and then they finally give up the ghost, and water gets into it. And the problem is that when that happens, the creeping crud makes a diode in there. The next thing you know, every time your transmitter goes on the air, it's generating this spectrum of signals that kills everything. So please do whatever you can to keep water out of the antenna, and check it out. Watch out for Permatex. The stuff is not do that. Watch out for acetic acid, not good. 3M Scotch Coat and 130C is the sort of the gold standard for how to do this stuff. All right. The other problem is when water gets into the phasing harness, it doesn't show up on the SWR, because now all your energy is going to one of the elements in the antenna instead of all of them. And guess what? When you go to one element instead of 4, you end up with a good SWR. But the signal gets weaker and the directional pattern is kind of funky. Okay, so we got to watch the this thing here. This thing works because the coax lines have critical lengths. If one of them cracks, you can't just splice it. You got to really replace it. The horizontal pattern is determined by how you space the elements. Just watch out for moisture. And here we have a very simple formula for the impedance on your phasing harness. And it's the square root of some of these sections over here. A lot of times the impedance into these antennas is a weird one. 35 ohms is common. So it's hard to find RG141 to put that into a phasing harness. Sometimes that's a special order. It can take a long time to get there. So it pays to have a short length of that, 50 or 100 feet of this stuff in your toolbox so that when you need it, you'll get it. Okay, and also pays to have some other things. Certainly 75 ohm is in the cable TV industry. That stuff is common. 50 ohms is the sort of the standard for ham operators and most RF stuff. And then there are other strange things. 93 ohm coax was once upon a time popular in the data industry for connecting data terminals to controllers. That stuff has seemed to have gone away. But you can find it in phasing harnesses sometimes, depending upon how it's designed. So just make sure you have replacements for that stuff. Okay. More notes, we talked about moisture, being exact about the phasing harness. Moisture problems only show up under full power. So your antenna analyzers, your devices we commonly use, the nice ones that come from Ukraine, they don't have enough power in them to induce faults, especially those caused by moisture, flexing vibration or water ingress. With several elements disconnected, the SWR does not look terrible. So we have to watch out for that. Now, an antenna method that we have to use to see if it's working is sweep it with some power and look at the 2-to-1 SWR limits. And hopefully you've done that when you installed it in the first place. And now under power, you can look at it again, look in your logbook to see if something changed. So let's get to the thing of a logbook. An antenna logbook, when you put it in, note your forward power, your antenna power, your return power, SWR, and check it out once a year. Make sure it's good. And remember, you got to check it out with power. And watch out for rules and regulations here, but make sure you identify who you are when you're doing that and do it for a minimum amount of time, preferably at a time when people are not likely to be using the spectrum. Okay, logbooks are vital. Okay, we talked about something before called down tilt or beam tilt. And literally, mechanical down tilt is you bend the antenna in such a way. Don't recommend it. Half your antenna goes out to feed the birds, and the other half goes down into half the listening area. It makes the pattern look pretty ugly. And some cases it actually works, and people can use this. But we usually use electrical beam tilt. And we work that out by varying the phasing between different antenna elements. And beam tilt is used to make the signal go down in all directions. And this is used when we have a very high sight. I would suggest that if you're less than 300 feet, depending upon your terrain, it's probably not going to make much of a difference. I would not pay too much attention to electrical beam tilt until we get above 300 feet. Certainly people at Empire and at, Trade Center type heights, the Freedom Tower, there you really need your electrical beam tilt, because what this does is it pushes the signal down to your visible horizon. And it makes the signal more strong for most users instead of skimming above them and, making the birds all a little bit warmer. Okay. Sometimes we have to put antennas inverted. We put them in upside down. Okay. And at that point, you got to make sure that the supplier of the antenna understands that the mount has to be down. That'll affect down tilt, because obviously in this case it would be up tilt. And you also have to put the moisture, what they call weep holes, in a different spot if you put your antenna in an inverted position. Okay, guys, gas discharge tubes. This is just kind of miscellany here. Normally open devices with not shunting a surge event. However, they degrade over time. They typically have a 20-year shelf life, after which you probably ought to replace it whether it needs it or not. And during its lifetime, they typically have a 20 amp total surge capability, which accumulates. And if enough of that happens, they fail open. Ouch. If it fails shorted, you'll know it right away, because the SWR will be terrible and your transmitter won't be able to stay on the air. But if they fail open, it just stops protecting you. So don't let that happen. Replace these regularly. Okay. Coax. Let's talk a little bit about coax. Okay, we have a loss per unit length, the dB loss, and that's going to be a function of what frequency it's at as well. Okay, we have a diagram over here of coax, pretty ordinary. We have a dielectric insulator with the dielectric constant by this funny looking Greek letter. We have the D, capital D. This is the center core. I'm sorry, yeah. And center core is D. Big D over here is the metallic shield. This is, big D is the inner diameter of the shield. Center core, small d, is the outer diameter of the center core. And that's going to deal with when we get down here with skin effect. The current flows on the skin of these things. In the case of the coax, it flows on the inside of the braid or the shield and on the outside of this center conductor here. By the way, on those coax pictures we saw before, that's why a lot of them can be hollow, because the signal is actually on the inside, not on the outside. Okay, coax has specific impedance, which is basically the square root of the ratio of inductance to capacitance. And here we see another way of writing the formula for that. It has a specific power handling capacity. It has a breakdown voltage. You have to pay attention to, especially the broadcasters. This stuff doesn't mean much to ham operators because these limits are way beyond what our repeaters will do. We have to pay attention to the dielectric material because that also affects the propagation velocity and the loss of the coax. Capacitance per unit length on most coaxes that we use, it's about 30 picofarads per foot. Get that number from the manufacturer, but most of them seem to converge at that number. The velocity of propagation is the speed of light in the coax. It's slower than if you do it in free space. And that number is a function of the type of dielectric that you use. Okay, so a foam type dielectric is going to have a dielectric factor of 0.7, 0.8. Polyethylene foam, pretty common. Their dielectric is going to have a velocity factor of 0.6 or so. If you have air insulated coax, it goes up to 0.95. So they've got to watch and pay attention to that. Okay, I mentioned skin effect, where the current flows on the inside of the outer conductor and on the outside of the inner conductor. And here is a rule of thumb style formula to let you know how deep that is. Okay. Then we have an issue called percent shield coverage. When you have a braid shield, especially those from not reputable manufacturers or somebody buying cheap coax, the braid isn't woven tightly, and you can actually see the dielectric on the coax through openings in the braid. 40% coverage is typical of that stuff. Don't buy it. Get rid of it if you have it, please. It's terrible. The only thing it's good for is CBers, and you know, they're pretty much gone anyway. Foil shielding is good. Usually you see a foil shield in combination with the braid. If you want to see really good coax, there's 2 foil shields and 2 braids, concentric with each other. And typically that type of shielding has 99-point-something% shield coverage. Waterproofing, some coax has to be outside. So you want to make sure that it's resistant to water getting in it. On the other hand, if you don't run it, if you need to run it through an open water, you better get coax designed for that purpose. Resist UV, the materials you make the jacket out of will affect its UV resistance. Bend radius, when you have to change the direction that the coax is going in, you need to pay attention to how sharply you can bend it. 10 times OD is safe, 10 times the outer diameter. So if you have a 1-inch outer diameter coax, you know, fairly common, you need to make sure that your bend it is going to be at least a 10-inch radius bend. The bend it's tighter than that, it may kink the coax and producing an impedance bump. Tightest I've seen coax bent in is 4 times OD, and that can get to be pretty dangerous. Don't recommend it. The other factor about using coax is make sure that you can get connectors for the type of coax that you do choose. Okay. We have to make sure that we have low passive intermod on our RF interconnects. And this is distortion caused by high power signals. And for us hams, that's when we get into the 100-watt and 250-watt class. For broadcasters, it's just about everything you have. Distortion and noise generated by your high power signals interacting with nonlinear RF paths. If they exist on the same thing, lo and behold, you have a nonlinear thing. It's called a mixer. The next thing you know, you have sum and difference frequencies, which are going to raise the noise floor at the site. And worse yet, they may be intermittent, or the thing may come and go according to which way the wind is blowing. Tough to find, and everybody's going to be pointing the finger at somebody else. Very difficult to find that. Workmanship is key over here. You've got to find somebody that knows what they're doing really well to put the connectors together and put the coax together. And generally speaking, factory-made coax works better than stuff you do in the field. All right.
Hey, George,
Yeah, go ahead.
I want to allow some time for some Q&A. So I know in your original presentation you had like 36 slides. I don't know if we're going to make it through all of that, but
If you want me to speed it up, I'll do that.
yeah, if you would, because
Sure.
I believe I'm getting some text or maybe some questions.
Okay. Hey, no problem. Well, let's move on then. Okay, duplexers. This is what allows us to share an antenna. And the most common thing is that it saves an antenna, it saves feed line and rentable tower space. So people want you to only use one antenna since you're paying for the space to put one. So this is what the duplexer does. Also, when you have the same antenna, you'll have common antenna patterns for your receiver and transmitter, which are good. So we put in these very high Q filters, closed cavity filters, and these things are substantial in size. The particular ones that I've pictured here are roughly the size of scuba tanks. These are roughly 5 feet long and 8 inches or so in diameter. There's two types, a band pass and a band reject. And here we see that they're wired differently. We have pictures of what these things look like. All right. The cavity size is the function of the way it's built and the material it's made of. Okay, and here we see schematic diagrams of the two types, the band pass and the band reject. And the different type of circles inside these things, we have things, most good duplexers for repeaters have a combination of band pass and band rejects. 4 cavities about the minimum, 6 cavities is pretty common. Okay, cavities are relatively expensive. They're somewhat temperature sensitive. The tuning rods on these things basically have a plunger that goes up and down, changing the length of the rod. Tuning rod is made of Invar, which is a metal that doesn't change its length in response to temperature changes. And you notice you have compression set screws to tighten them down so that people don't come, oh, this screw is loose, and tighten it. There goes your duplexer. So these things are huge, and just be careful with them. Okay. Circulators or isolators, and this is stuff that you see on repeaters. You don't usually see them in other things. This is basically a one-way valve for RF energy. Isolator is the circulator with a dummy load attached to it. They're physically fragile. They depend upon having very high power permanent magnets and ferrite toroids in them, which are basically concentrators for magnetic field. They're brittle, they're sensitive to shock, they're very sensitive to temperature. They overheat. When they overheat, they crack. So you got to be very careful with these things. They're sensitive to nearby magnetic fields. You have to be careful about where you mount them. If you're mounting them on something that's magnetic, it's going to detune them and they won't work. So typically we mount them on aluminum panels with non-ferrous hardware, meaning brass screws. If you use steel screws, it'll actually affect the tuning on these things. So don't do that. When we buy them, they come in multiple stages called an intermod panel. All right, and this tells you where we put them. Circulators will generate harmonics due to nonlinearities in the ferrite. So they cause intermod, but they prevent more than they cause, so we use them. And the manufacturers typically put band pass or low pass filters in the same box with the circulator. Don't connect it directly to the antenna, and they require tuning. And there's trade-offs in tuning between insertion loss and return loss. Best practices usually favor better return loss versus insertion loss. Okay, here's a picture of what one of these things looks like. This is the dummy load, this thing here, 125 watts or so. This is the actual device. It's in this box along with low-pass filters. And the rest of this is just a patch panel for your RF to go through. This is an aluminum tray, good for heat sinking and good for not screwing up the way the duplexer works. The front panel is steel. Okay, so we have some specs for this thing. Here's a diagram of how this thing works. It's a series of very high power, usually neodymium or other rare earth magnets, going into some strip lines on a PCB. And this is almost like black magic. The permanent magnets give it a bias that force the field traveling through this junction to only go one way. All right, and there's a whole series of things on how you do these. If anybody's interested, it's a whole art in itself. Typically, we buy these as manufactured components. Most of us on the ham side don't try to build these things. Okay, now we get to some more mundane problems that all of us face, which is where do we get our power from? So we have commercial power. Many of our sites have generators, but these days there's a lot of pressure to be ecologically friendly. So we have voltaic, wind, and fuel cells, and UPSs with batteries to provide our power. And here's a picture of a typical site backup generator. This is the one over at the WLIW transmitter site over in Plainview. When we do that, we need to have a transfer switch to go from backup power to mains power and backup. These are usually automated. And typically there's a typical break before make function on these transfer switches. And there's maybe as much as a few seconds. So you better make sure that your repeater and your electronic gear can withstand a few seconds of a delay while you switch from one source to the other. All right. And these are the different loads typical in a repeater environment that you have to take care of. Watch your circuit breakers, arc fault ground protectors are usually called for in code. Could make sure too that you have EMI and surge protection on these things. And here's one that usually gets most people. Andy, this one is for you. Yeah. Make sure that your power to your system is going through a twist lock connector so that somebody just can't walk in, unplug your transmitter and plug in their floor cleaner. Clean the floor and then forget to plug your transmitter back in.
That's okay. They don't clean the floors over here, so it's fine.
In your office, yeah, but in room 13, okay.
Hey, George, we're almost out of time here. We definitely want to be able to take some questions. So I hate to cut you off, but we can't go too much later because.
Okay, let me go a little faster. Okay, here we have a picture of the receivers. Yeah, the thing in a repeater are the aperture coupled helical resonators, which are narrow band. And here you see what they look like when they're assembled. Block diagram. The transmitter, phase noise is a problem. So we do lots of things to watch out for phase noise. How we work around SWR detection. We have foldback. So if the SWR rises, it cuts down the power automatically. Electrical design best practices. This is really important for all of us. I suggest we look at it. This is called D-rating on the left. This is called really good circuit design with high Q circuits on the right to eliminate phase noise. We have controllers that help us enforce FCC rules, which is why we do this. So you can control it locally, so you control it over the internet. And there's the different devices and things that we do. Like anything connected to the internet, we have cybersecurity, things that we have to watch out for. Backhaul and linking, like I said, our repeaters don't stand by themselves most of the time. We have internet interfaces through Ethernet, Wi-Fi, or cellular. Programs we use to do this, All-Star Link, up and coming. This is what we use on Long Island for LIMARC, the Great South Bay Network, and a bunch of other repeater networks. It's very popular and it uses voice over IP. We have Echolink, which has been around for a while, that helps us link cell phones to repeaters. I have one, I could demonstrate it. Then we have Internet Radio Linking Project here, VHF, UHF links. These are just direct links. We have Wi-Fi, Meshtastic is one, there's optical links, lots of stuff for backhaul. Security is really important. Most of us don't pay as much attention to security as we should, but when we do pay attention, it helps us reduce failures and improve our mean time between failures. Most of this stuff is documentation and then hardening a site, okay? For the hams, authentication and authorization are problems because we're not allowed to encrypt over the air. So FCC rules are pretty blatant about that. So we have issues when it comes to trying to do secure sign-ons. That's tough for us to do and make it truly secure. Okay, in this box here are future security things that we're in the process of doing. Laws and regulations. Here you see our FCC. We have specific rules for repeaters. Everybody has to obey the RF radiation exposure limitation. FCC Part 15, again, this is general. All equipment has to obey this. Part 17 is our tower lights and obstruction markings, and there's a 200-foot magic number. PRB 1 is a legal document that requires that local documents accommodate ham radio installations. Unfortunately, it's at the state level, and New York, Connecticut, and New Jersey has not adopted this, making it a field day for lawyers with helpless hams with nice towers. Okay, municipal building codes, they make a difference. Fuel storage. When the World Trade Center came down, we found out that there was a whole floor that was nothing but a giant fuel tank. Not good, so the fire department promptly proceeded to ban these things. And you have to pay attention to your local building codes to see where you can store the fuel for your generator. There's site-specific rules depending upon what site you're at. And then our trade unions often have things like union members have to do certain functions. pay attention to that because it may affect the way you have to install or service something. Okay, in Indiana, they have a repeater council. Here's a map of some of the repeaters in Indiana that are accommodated. And here we have a PRB1 that Indiana does obey. They've adopted this. So there is a minimal regulation, which is of hams. Future considerations, AI is one. I personally think the biggest use for AI is going to be in speech recognition. That's going to help our repeaters do all kinds of things, including over-the-air voice to commands, biometrics to recognize people so you don't have to encrypt something, speech translation for when you want to go into a foreign network and say we want to go up to Canada. The guys up in Quebec, they can talk to us in French and your AI will pick it up and translate it into English for us. That would be neat. The cardinal rule is to make sure everything is time-stamped and recorded. That's very important there. Future repeaters, we have voice as another bit stream. Single frequency repeaters are now feasible. It's been demonstrated, but the ham operators aren't there with this stuff yet. Open source software is becoming popular. There's an upcoming digital protocol called M17, which the ham operators are beginning to get into. And it'll give us a better quality and better signal strength at longer distances. We can aggregate channels, which we call channel bonding in the IT world. That'll give us greater bandwidth. Voice is just another bit stream, and you can change voice to other types of data when you're not using it for voice. The user radios can be open source designs that are cheaper and better than the ones. And we certainly encourage experimentation, new types of protocols. And again, I mentioned M17. And here we have some references, and I kind of blew through the second half of this thing much faster than the first. So anyway, thank you.
And will you make this available for anybody that would like to, your presentation here? I mean, we've recorded this as well, but you have some good slides here.
Great, thank you. I'd be delighted to send it to whoever is going to take care of that for you.
Okay.
All right, and Bud, I think you have a copy of it, and at one time or another, I gave Andy a copy. I'm not sure if he's.
Yeah, I have a copy, so anybody can ask me.
Yeah.
Bud@dre.cc or go direct to George, and I can get that information out if need be. Any questions? I see.
Bud, I was also going to say you could post it on your website. That would be fine as well.
We can do that. Yes, thank you. Any questions from anybody or any comments? How about KD2 AAR? You have any comments?
Who's that?
John Frex.
I know.
Hey,
Yeah.
Hey, there you go.
there I am. Yeah, oh, excellent presentation. I really appreciate the depth of the knowledge there, George. It's really probably more a event description of all the technical details, which most people just really don't quite fathom. Obviously, there are certain things about amateur radio that do apply to other broadcast level broadcasts and propagations and things. But yeah, it's fascinating to really get into the weeds, as they say, get into the nuts and bolts of why it does what it does. So, and like I said, a lot of research went into that, a lot of time and effort, and very, very well put together. Thanks, George.
Thank you.
Yeah, thank you. And it's funny because I noticed Walter Freeman is on as well, and Walter is, one of the smartest guys I know, and I'm willing to bet he learned something here. Walter, did you?
Oh yeah, Aeolian vibration. Beautiful.
Yeah, that's the Peter, Paul, and Mary song. The answer, my friend. Blowing in the wind.
A question I have that I actually get. It's not positioned in a way that is too technical, but the usage of bays to create the aiming of the zone of Fresnel. How is, the question is always like for WRHU, I could put this in maybe layman's terms. We have 4 bays on the antenna. So how come we don't just knock the bays off and go full power as opposed to keeping the bays and rerunning it at a lower power. And I try to explain it, but sometimes my explanation isn't so good.
Oh, okay, in simple terms, okay, if you had just one bay, you'd have a more circular pattern. I'm assuming these bays are circularly polarized,
Yes.
similar to your WRHU installation.
Well, that's what he's talking about. Yeah. So he's saying with a 4-bay on that FM, and you were talking about 4-bay dipoles. I think that may be a little different, but we're using, if not mistaken, 4 bays on the broadcast side to, narrow that pattern going straight out towards the horizon. Is
Yeah,
that what's
that's true.
happening with
Yeah,
those dipoles on your side?
Yeah,
The amateur side?
if you look at it, if you just had one, it would be closer to an isotropic, which is a point in the middle, and then the radiation goes out as a sphere.
Mhm.
So here's your power, okay? You have so much of it, and it's going up to this, and you're building this sphere of radiation. So the birds are having a great signal. Unfortunately, most of them don't appreciate it, even in the winter when they get a little bit warmer if they go near it. So the purpose of all these bays is to flatten that out, to bring the radiation pattern closer to Earth. So instead of looking like a sphere, it becomes looking more like a donut. Okay, and you're
Got it.
squeezing the balloon, okay? There's only so much power going into it, but when you squeeze the balloon, it gets wider around the belly and the top and the bottom get compressed. And guess what? That's good, because you don't need a super strong signal right in the building that you have the antenna in. It's okay to lose that. They're going to pick up the signal anyway. The birds aren't going to care. They may be grateful that it got a little colder up there. On Long Island here, with omnidirectional antennas, we have a problem with feeding the fish, as you saw from some of my diagrams. So we like to kind of compress the signal so that it lines with the land masses on Long Island. And that's why we do that. It saves us power, which is ecologically a good thing to do. And it lets us use less expensive components. And it works pretty well. And yes, you'll get more signal out in more kinds of places, usually places you don't want the power if you don't do that. So, hello, what do you want? By the way, I had a big problem back in the days when I worked at WLIR, mostly because I was this high school kid trying to argue with the station owner that he didn't want to warm the birds with his antenna. We ended up with a 2-bay circularly polarized antenna, which basically meant we had a gain of 0. Neither gain nor loss, but we had to feed it with a lot of power. And I could have saved him half the power he was using if we had gone to a 4-bay antenna. He didn't want to do it. Go figure.
Pros and cons all the way around.
Yep.
Any other questions from anybody?
Anybody use repeaters? I mean,
I know there are.
Well, certainly, being an amateur radio operator myself, and being involved with a couple of different clubs, I'm actually the repeater trustee for a couple of 2-meter and 70 centimeters over in New Jersey. So there you go. I certainly do use repeaters there, George.
right there. Okay, I'm certainly using them too. And by the way, I'm the trustee of a Grumman repeater. Its call sign is WA2LQO. We have 2 of them. One is on Andy's premises, and he didn't know I was the trustee, but that just happened. The other guy died in an unfortunate car crash. And I also end up being the trustee of a lovely repeater with a 700-foot tower height above sea level out in Hoppock, which is, I'm pretty glad to do that, but that's another Grumman Club tower. And Grumman and LIMARC are affiliated, and I'm a vice president of LIMARC, and today LIMARC is running 11 different repeaters. So yeah, we got a bunch of them.
Well, thank you, George. I appreciate the effort you put into this and the knowledge that you shared. A lot of this does apply with broadcast and whether radio or TV, FM. I've learned a number of things. I'm sure the guys have as well.
Thanks for joining us. Please remember to subscribe to SBE 15 New York City.